Okay, this homework set that I'm going to do here is actually for my internet class, but it will help any of my Cal 2 students. So working out of the homework for the internet class, I'm going to start with, this is for section 7.2, number 2. So it says to find the volume of a pyramid whose base is a square. So you have a pyramid, the base is a square, the side of which is L, so L all the way around. It's a pyramid, and they're telling you the height, from the center up is H. It says to find the volume of this. All right, so what we're going to do is we're going to imagine laying this pyramid sideways. Okay, so it looks like this. All right. Just looking at it straight from the side, we know, and I'm going to orient it onto the XY axes like this. We know that the distance from here to here is L. We know that the distance from here to this point is H. So that's the point H right there on the x-axis. And let me make sure my video is recording here. Okay, it looks good. All right, so imagine now that we're going to take a bunch of slices, so a bunch of infinite slices of this. If I take one of those slices and look at it, it's a cross section of this pyramid, it's kind of like taking a slice out of here, and I'm going to find the volume of that little slice. So imagine the little sliver of the pyramid. So to do that, I have to take a slice from in here, and I have to determine over here in this picture what the volume of that slice would be. And then I'll add up all those slices, and I'll go from 0 over to H. So we know that this side, whatever it is, I don't know, I'll just call it S, is equal to this side S. And we know that this is dx. That's the width of the little sliver. So if we can just figure out what this side is, we know we can find the volume. But that side is not L. L is only the very end. So we need to figure out, this distance. So to do that, I'm going to use the fact that I know a little bit about this line right here. This point right here has the coordinates H, and then if the whole distance from here to here is L, then halfway will be L over 2. And I have another point, which is this one, and that's the point 0, 0. And so the equation of this line can be obtained by using the formula y minus y1 equals m times x minus x1. The slope of this line is y2 minus y1 over x2 minus x1. So it's y2 minus y1, which is 0, over x2, which is h, minus 0. So this is L over 2 over h, which is the same as L over 2h. That's the height, that's the slope of this line. So it's L over 2h. And then I just need to use one of the points and plug in here, and I'll just use 0, 0 because it's easy. X minus 0 over here, y minus 0. So the equation of this line is y equals L over 2h x. So that means that the height from here to here is going to be L over 2h x. It's the y coordinate of this point right there. And since I want to know this entire length, it's going to be the same thing, right? L over 2hx. Double that, right? So if I double this, take 2 of those L over 2hx's, multiply by 2, I just get L over hx. So this side, S, is actually L over hx. And this side's the same thing, L over hx. And so the volume of this little sliver is this times this times this. So dx is at the end. When you do this, you basically square it, so you get L squared over h squared x squared. And so what I want to do is I want to add these up. I want to add them up forever, or an infinite number of them, and I want to move my sliver from 0 to h. So kind of should have pointed this out earlier. This is not a solid of revolution problem. This is something different. So the volume of the pyramid should be the integral from 0 to h of L squared over h squared x squared dx. And L squared or L and h are constants in the problem. That's the pyramid that's already given to us. So I can pull the constants out of the integral, and I can just integrate the x squared. So this becomes L squared over h squared times the antiderivative of x squared, which is 1/3 x cubed, evaluating from 0 to h. So now what I do is I replace my x with h, so I get h cubed, so L squared over h squared times 1/3 times h cubed, minus, now plug in 0, everything goes away, you get 0. And then we clean this up. I can cancel out 2 factors of h, that makes that just an h, and that gives me my final result, which would be 1/3 L squared h. All right. Okay, the next one I want to do is number 8. So it says find the volume of the solid rotating the region bounded by y squared, it's number 8, y squared equals 2x, x equals 2y, about the y-axis. So this is a solid of revolution problem. I need to draw out these curves. So I need to determine if I'm going to look at these as functions of x or y. But I'm going to be rotating around the y-axis, which means that my rectangles are going to need to be sideways, horizontal. So I'm going to be needing to solve these for x. So solve that for x, you get x is going to be 1/2 y squared, just dividing both sides by 2. This one's already solved for x, so I'm in business. So I need to graph both of those. So let me go ahead and do that now. Let's graph this one because it's a line. If y is 0, x is 0. If y is 1, x is 2. And it's a line, so I can just draw. Okay, that's x equals 2y. Now to draw this one, if I let y be 0, I get x is 0. If I let y be, let's be clever here. Well, let me do 1. If y is 1, then x is 1/2. Let's see, remember this was 2. So here's 1, it'll be here. If y is, I'm going to try and pick a nice one here, 4. 1, 2, 3, 4. If y is 4, sorry, I meant to say 2. If y is 2, 2 squared is 4, 4 divided by 2 is 2. So if y is 2, x is also 2. And then if y, should I do another one? If y is 4, should we do that? 4 squared 16 is 8. So if y is 4, it's 8. It's way over here. So we've got this parabola going like this. And somewhere it looks like they're going to hit each other. Somewhere. I don't know where. And so I've got my region in here. And I'm trying to rotate that around the y-axis. So my rectangles are going to need to be sideways like this. And so I need to know to integrate from, what y value, from 0 up to where? Wherever these hit. And I'll have to figure that out later. But let's just set up the actual outside radius and inside radius first. So I'm going to transpose this down. Here's my axis of rotation. I bring the rectangle down. And then I have my red one is going to be on the right. My blue one is on the left. And so I stand at the axis of rotation, I look out, and I look for the outer radius, which is from here to here, which is the red function, which is actually 2y, because remember it's a function of y. And then the inner radius is from here to here. That's the blue function, which is 1/2 y squared. So this is my outer one, and this one right here is my inner one. So I'm almost ready to set up the integral, except for the fact I need to figure out what this limit is. So I have to set these two equal to each other. So I'll do that now. I'm going to set 1/2 y squared equal to 2y. When I do that, I'm going to multiply both sides by 2. Y squared is 4y. Subtract 4y on both sides. I factor a y. And I set equal to 0. I get two answers, 0 and 4. So up here at 4, this is where they hit each other at 4. That y value is going to be where I stop my integration. Of course, it started at 0 and then went to 4. All right, so now set up the integral. This is going to be, the volume is equal to pi, integral 0 to 4, outer function squared minus inner function squared dy, because our rectangle is horizontal. So the outer one is 2y, and the inner one is 1/2 y squared. And then you square them and you go through all the integration, which I'm not going to do. All right, hope that helped. All right, the next one I want to look at is number 9. So for number 9, give you y equals 2e to the negative x, y is 2, x is 2, and you want to rotate this about y equals 4. So I'm going to start with my graph of my region. All right, let me start out with let's take care of the easy ones first. Y is 2 is a horizontal line through 2. X is 2, the vertical line through 2. And then y equals 2e to the negative x. So let's plug in 0. If we plug in 0, we get e to the 0, which is 1. 2 times 1 is 2, so it's right there. And if I plug in a number like 2, e to the negative 2 is a really small number, times 2, small, so it's going to be like this. And then it's an exponential that's been reflected, so I kind of already knew that, but this is the graph right there. So the region that we're talking about is this region right here. We want to take that and we want to rotate it around the line y equals 4, which is up here. I'm going to rotate it around that. So my rectangle that I'm going to use is going to be in here. It's going to be vertical, and I'm going to wrap it around like that. So come over here and I draw axis of rotation. My x-axis is down here. And what do I have there? Red, green. So my green one's on the bottom, red one's on top, green one is on the bottom. This. So I need to find my outer radius and my inner radius. So I'm standing on the axis of rotation, which is up here. I'm looking out, trying to find the outer radius, which is that, and the inner radius, which is this. Now, because the x-axis is here, I know that the distance from here to here is the 2e to the negative x. I know the distance the entire way is 4. So the distance from here to here will be the 4 take away the 2. So this will be 4 take away the 2e to the negative x. Same exact story here. The distance from here to here is 2. That's always the same, right? Because the red stays the same the whole time. And if the whole distance is 4, then that forces this to be 2. Never changes. So we have the outer one here. We have the inner one here. Now our limits of integration go from 0 to 2. And so we can go right to the integral. So volume is pi integral 0 to 2 of the outer function, which is 4 minus 2e to the negative x squared minus the inner function, which is 2 squared dx. And you have to square this, so you have to FOIL it, and it should all work out. The integral on that's not too bad. You're just integrating e to the negative x. We've done that before. All right. What else? Okay, number 11. Y equals 3 sine x, y equals 3 cosine x, 0 less than x, less than or equal to x, less than or equal to pi over 4. And you want to rotate this about y equals negative 1. So let's start with a picture. All right. So when we look at 3 sine x, that's a sine curve with an amplitude of 3. So we know that sine, if we go out to 2 pi, sine should go like this. Up, down, back up like that. Now we are only looking between 0 and pi over 4, which is right here. That's pi over 4. So my graph, I really don't need this whole thing. So I just wanted to point out this is what sine looks like, and our amplitude is 3, so we know that that's 3. So what I'm going to do is I'm just going to kind of blow this graph up a little bit, just to make it a little bit easier to look at. Here's pi over 4. And let's say this is 3 up here. And we knew that sine started here, that it went up and hit its peak right there. Okay, right at the pi over 4. Now cosine, 3 cosine is, remember if you graph cosine, cosine looks like this to 2 pi. So we're only going to be looking at, let's see, cosine of pi over 4, we're going to be looking right in here. Oh shoot, you know what? Hold on, it's pi over 4, not pi over 2. All right, this is not correct. This is pi over 2, I apologize. This is pi over 2. So pi over 4 is in here. I don't know why I did that. So this is the correct sign, but it goes to the top at pi over 2, not pi over 4. I don't know why I did that. All right, so cosine, 3 cosine of x, would start up here, and at pi over 2 it would be 0, so it looks like this. Okay, so this is pi over 2. Pi over 4 is in here, so somewhere in there they hit each other like that. And we're trying to find the region bounded by these. We're told that the x value has to be between 0 and pi over 4. So here's 0, here's pi over 4. So we're looking at this region in here, right there. And we want to rotate that about the line y is negative 1. So y is negative 1. down here. That's our axis of rotation. So I'm going to use vertical rectangles like this. Take those and wrap it way around this line down here. So I'm going to transpose that over here. Here's my rectangle. Here's my x-axis. Here's my axis of rotation. I have the blue function on top, which is the cosine curve. I have the red one on the bottom, which is the sine curve. I'm going to stand on the axis of rotation, look out to the far edge of my rectangle, which is way the heck out here. Find that, and then I'm going to find this one. So we know that the distance from the x-axis to the blue, that's 3 cosine x. But then we need to add this distance. And this distance from here to here is always going to be that distance, which is 1. So I'm going to take 1 and I'm going to add to it the blue one, which was 3 cosine x. So the total distance is 1 plus 3 cosine x. Same thing with this one. From here to here is 1. From here to here is 3 sine x. So this distance all the way from here to here is 1 plus 3 sine x. So this one is my outer. This one is my inner. My limits of integration go from 0 to pi over 4. So we've got volume is pi integral 0 to pi over 4. Outer function 1 plus 3 cosine x squared minus inner function 1 plus 3 sine x squared dx. And then you would FOIL these out, and you're going to have some sine squareds in there, some cosine squareds in there. You're going to have to use the half angle identity. That's a tough integral. Not tough, it's just a long integral. But I've got it at least set up for you. Let's see what else. Number 12. Number 12 says that it says find the volume of the solid described here. The base of S is the region enclosed by y equals 5 minus 3x squared and the x-axis. So I've got a region that's created from those two things. It says cross sections perpendicular to the y-axis are squares. We're supposed to find the volume of this solid. So let's try and draw a picture. First of all, let's look at the base. All right, if we call this x and y, we need to graph this thing. So we've got the x-axis here, which is creating one of our bounds. We've got this parabola. This parabola is a parabola that opens down because I have a negative 3 and has been moved up 5 because I have plus 5. So up here at 5, it starts and then it comes down like this. Down. So the region that we're talking about is this region in here like that. And it says now that the cross sections of this solid perpendicular to the y-axis. So if I come in here and I take a cross section that's perpendicular to the y-axis, I'm talking about a cross section that's like this. Imagine a little infinitesimal cross section of that. When I look at that cross section in three-dimensional space, it's a square. So let me try and draw three-dimensionally to help you see this. This is x, this is y. So our parabola is on the ground here. Here's 5 up here. And the parabola comes down like this. Like that. Crosses through our x-axis. We have our blue x-axis here. So that's like this sheet laying down on the ground. Our region is in there on the ground, right? And when I take this cross-section, that cross-section comes across like this, has a little thickness to it, goes up, creates a square. So go straight up, over, and down. Has a little thickness to it like that. So that is that's what a cross-section looks like. And if I get a cross-section that's a little bit higher up, like here, then in the back, it's behind this one, is going to be a smaller little square. And of course, this cross-section down here would be really big. So what I'm trying to do is find this volume of that. So what I'll have to do to find the volume is I'll have to figure out what the formula is for the volume of one of those slivers. And it needs to be in general, and then I'll have to integrate, add them up forever. So let's take a look at one of those slivers. So let's talk about, we know it's a square, so whatever this is, that is. Do we know how thick it is? Well, that thickness comes from this thickness, and it looks like since my rectangle is horizontal, I'm going to have to be integrating with respect to y. So I know that this thing is dy. So how wide is it though? Well, I have to come back over here and I have to figure out the distance from here to here. Well, there's a problem with that because right now this is a function of x, so I can tell you what the height is, but I can't tell you this. So what we'll do is we'll take this and we'll solve it for x first. So let me move the 5 to the other side, trying to turn this into a function of x. I'm going to swap sides on the equation, like that. Divide by 3. Take the square root. Like that. Now I should do plus or minus. The positive one will give me this one, the minus would give me this one. So I'm going to say that this distance from here to here is root 5 minus y over 3. That's the x value. If somebody gives me the y value, that's the x value. And now that represents just this distance. By symmetry, the other side is double that. So I just double this. So that means this side right here is 2 of the root 5 minus y over 3's. But if that side's that, then this side's the same thing. And so the volume of this will be this times this times this. So the volume of that sliver is 2 times 2, which is 4. The root times the root goes away. And then dy. That's the volume of one sliver. And I want to add them up forever, or add up an infinite number of them. So if I add up an infinite number of them, I'm going to need to know where to integrate from. So as I move that rectangle, the rectangle moves up and down, so the y-coordinate is changing. And it's pretty obvious that the y-coordinate is going to start at 0 and stop at 5. So the volume of this will be the integral, not pi, because it's not a surface of, a solid of revolution, 0 to 5, and then this formula, I'm going to clean that formula up a little bit, pull that 3 out, pull the 3 out in front. That formula, dy. So that's it. That, whatever that is, you can figure out what that integral is on your own. And make sure I covered that properly. There you go. Okay, last one that I'm going to do is number 15. 15, y equals 5x, y equals 5 root x. And we're rotating this about y equals 5. I'm going to go quickly through this. Y equals 5x looks like this. Y equals 5 root x looks like this. They hit each other at 1. Check it for yourself, plug 1 in, you get 5 on both of them. And so the region that you want to integrate is this one. You're rotating around y equals 5, which is up here, right there. And so your rectangle is vertical like this. Here's your rectangle. Here's your axis of rotation. This distance is the 5, and take away the bottom function, which is 5 minus 5x. This one, that's terrible. This one, the inner radius, is the 5, but then take away this curve, which is the 5 root x. So this is your out, this is your in, and then you set up the formula, integral pi. We're going to integrate from 0 to 1, the out squared minus the in squared, and I'll let you finish it up. Out squared, in squared. All right, I hope that helps out a little bit on that 7.2.